So this module is about wave-particle duality, first proposed by Louis de Broglie. So remember, Einstein said that E equals mc squared, and then in this last module we talked about how if we replace E with the energy of a photon, hc over lambda, we come up with this equation here. The mass, an equation that describes the mass of a photon in terms of Planck's constant, its wavelength, and the speed of light. That is, we said that a photon has relativistic mass. Well, what this guy de Broglie did, he said, all right, if that's true for a photon, why can't it be true for anything, why, and actually vice versa. He said, why can't any particle with mass m and velocity that's moving at a velocity v have a wavelength? And he proposed this equation right here. This, for any particle at all, anything that has mass and is moving has an associated wavelength, according to de Broglie. It's pretty strange if you think about it. What he's saying is that your car traveling down the road has a wavelength associated with it. But as we'll see in a moment, it's been proven. So let's first of all do a couple of examples using the de Broglie equation. So let's calculate for an electron traveling at 5.19 times 10 to the 5th meters per second, not an unreasonable velocity for an electron. Let's calculate what its wavelength is. So all we do is use the de Broglie equation. Oh, by the way, make sure you memorize the de Broglie equation. Planck's constant divided by the mass of an electron. Remember the mass of an electron is 9.109 times 10 to the negative 31st kilograms. Planck's constant here. And there's the velocity. And we get 1.40 times 10 to the minus 9th meters when we plug in. Again, put it into your calculator, please, and check and make sure you get the same answer I do. Remember, a joule is a kilogram meter squared per second squared. That's how the units cancel out correctly here. Or, so this many meters, or, because 1 times 10 to the minus 9th meter is 1 nanometer, that's 1.40 nanometers. So pretty small, but, this is maybe a really high energy X-ray, gamma ray. Now let's look at a bullet, and let's say it has a mass of, about 4 grams, 0.00447 kilograms, traveling at 975 meters per second. If we plug these numbers, these are reasonable numbers for a rifle bullet. Plug these in, Planck's constant, the mass of the bullet, the velocity, speed, we get 1.52 times 10 to the minus 34th meters. That's a really, really short wavelength. We have nothing that we could possibly use, currently anyway, to measure something this small. The smallest things we have are the smallest wavelengths are gamma rays, which are a lot larger, a lot longer than this. So even though this bullet theoretically has a wavelength, it's not something that we can observe. So how do we know that it's that de Broglie was right? Well, Davison and Germer did this experiment, not this one right here, but a similar one. So this gets the point across. So one of the wave-like properties of a wave is that a wave can be diffracted, or can diffract. Get constructive and destructive interference after it passes through a hole. And this is X-rays, shined, passing through aluminum foil. And the bright spots you hear are constructive interference, and the dark rings, rather, are destructive interference. This is definitely light acting as a wave. Remember, X-rays are a form of electromagnetic radiation, which is light. Now let's look what happens when we hit that aluminum with a beam of electrons. We get the same sort of pattern. It looks a little, it looks different, but it's still definitely diffraction. They get bright spots and dark spots, constructive and destructive interference. This right here is a solid example of electrons acting as waves. So wave-particle duality, de Broglie's equation, lambda equals h over mv, remember it? And it says that any particle that has mass m and velocity v also has a wavelength associated with it.